Okay, shall we start again? Um, okay, so we had this. Okay. Um, now, um, we'll get on. Yes. Okay. So there we have Clausius again. Actually, so the last sentence of the of his article where he introduced the concept of entropy. Actually, he didn't say the entropy of the universe tends to a maximum. He says the entropy of the world tends to a maximum. But in the sentence before that, he made clear that when he says world, he means the universe. Okay, so that's. But anyway, so he says that. But as I said, he didn't define what he meant by what entropy actually meant. And so this is where we have to. So what is because I mean it is it is an observation. Oh, sorry, I have to start my clock, otherwise I keep on talking forever and ever. But actually now it's a bit less. Usually, so when we stop like at 35 minutes, 7:25. So it's late. Okay, so I'll keep an eye on my clock because I don't want to rob you of your meal. Okay, so the thing is, it is not. I mean, if you say why does heat flow from hot to cold, I mean, everybody says, well, it does, doesn't it? Well, but that's not good enough. And so, what happened towards the end of the 19th century and the beginning of the 20th century is that we got a physical picture uh, that explains why heat flows from hot to cold. And that story starts with another happy-looking gentleman. This is Ludwig Boltzmann. As you may know, he committed suicide in 1906. People say that he did that because people didn't believe in the atomic hypothesis. I think the evidence is actually very minimal that that's true. Um, the thing is that um, in the 1850s to 1870s, maybe even earlier, the atomic hypothesis was generally accepted. So it's not that Boltzmann was considered too modern, he was considered too old-fashioned. Because towards the end of the 19th century, people started thinking that all these things like atoms and molecules, they are like simple images that people use to rationalize things, but they had no real physical meaning. And Boltzmann, who of course had been trying to predict the properties of transport properties of gases, cared very much about the atomic picture. So he tried to convince people that actually no, it is something you really really need to in order to be able to explain natural phenomena. So so towards people like Mach and Helmholtz and no no not Mach and Ostwald were very much against this whole idea of uh, of atoms. So Ostwald once wrote that believing in atoms is like worshipping idols. He thought it was a totally unacceptable thing to do. So yes, Boltzmann was under pressure, but at the same time he had some powerful friends or friends who were emerging and would be powerful. People like Einstein and Planck, who were great fans of him, and so I don't think that and that this was what in the end drove him to suicide. But the main thing is that Boltzmann was the person who first gave a probabilistic interpretation of entropy. And so if you go to Boltzmann's grave, you see here the expression S is K log W, uh, where basically this relates the entropy of a system to the logarithm of the number of states. And I'll come back to that because it is one of those expressions that you first accept and then start to wonder. But the thing that is actually curious about this SSK log W is the following: that Boltzmann, of course, had been doing a lot of work on the properties of gases. He had been constructing models of phase space, in particular at the level of individual atoms and molecules, where he divided the phase space up into cells. But he actually never thought in terms of really being able to count the number of states, because positions and momenta are continuous, so you can't really count positions and momenta in that way. And so the curious thing is that although this is Boltzmann 1906, it's not that true that quantum mechanics didn't exist at all, but it was only at that time Planck's his paper on the black body radiation, which at that point seemed seemed to have little relation with the kind of systems that Boltzmann was talking about. That you would think, how come that Boltzmann wrote this equation, and the answer is he didn't. So the what actually happened is that somebody else first wrote SSK log W. It's not a totally unknown person. Here we have it, somebody called Max Planck, who in 1900, this is published in 1901, wrote an expression where he said, actually in the sentence above, he said, inspired by the work of Boltzmann. So there's no doubt that Boltzmann's idea were crucial, but Planck wrote it down. He said, inspired by the work of Boltzmann, let's write the entropy of a system of n particles as k times the log of the number of states. And of course, Planck was talking about the number of states. When you say, so why is it on Boltzmann's grave? Well, the thing is that when Boltzmann died in 1906, he was buried in Vienna, but there was no monument on his grave. And so then, as I said, both Einstein and Planck were great fans of Boltzmann's work, and not, I mean, there are many others, but they certainly thought there should be something more substantial. But it took a while, actually it took a long while, almost 25 years, before they had the monument, was the statue of Boltzmann and his name, etc., etc. And then I thought, now we need a text. I said, well, what text should there be? And then Planck said, how about SSK log W? And by the way, this term had dropped out, and I think it dropped out at that point because since then Nernst had come around with the third law, and they thought this constant we can ignore, which actually you can't, but I'll come back to that later in the lectures. So this is actually how SSK log W ended up on Boltzmann's grave. I think correctly, because as Planck said, he was inspired by Boltzmann's work, but it was not really Boltzmann who wrote it. The unfortunate consequence, and I cannot completely admit it, is of course that when Planck died in 1946. Well, okay, so I think that we should correct that. My own suggestion is that we should do this, but okay, that's good. Now, the thing is that as I said, the Boltzmann entropy is a measure for the number of states in a system, and in classical mechanics, it is a measure for the accessible phase space. So you look at a system at n particles in a volume V with energy E, and then you can map out what hypervolume in this space, in the spaces of coordinates and the momentum of the particle, is compatible with these conditions, and that volume is then what takes the role of W, except that you have to divide it by something, actually h to the power 3n, to make it dimensionless. Now, the thing is that it is not at all obvious that these two things are the same, because I mean, so as I said, Clausius said that when heat flows from hot to cold, the entropy increases, and now we want to know how we can relate this to this statistical picture, or at least this counting picture, where you say that W is that S is related to the log of the number of states, and this actually is one of those things that where I would say the more I think about it, the less obvious it becomes. But maybe it's totally obvious. Good. So the the first thing that uh, you have to assume, although it is not, it is, I'll come back to it, it's not absolutely essential, but the first thing that you typically assume to get to this relation between entropy and heat flow is that you assume that if you have a system with energy E, volume V, and particles, and it has a large number of possible states, and now let's call them quantum states, that the system is equally likely to be found in all these states. In classical mechanics, the equivalent statement is that the system explores the phase space, the space of all coordinates and momenta that compatible with the conditions, uniformly with the same density. So the density in phase space, after if you wait long enough, is constant. That's and so that every point in phase space, well, I mean, a point is better not talk about this. Every small volume in phase space is equally likely to be visited in the history, very long history of a system. Now, the the thing is that this is first I say this and then I show why it's important, or at least why in the simple argument this is important. The uh, uh, the thing is that if you have a system, for instance, in classical mechanics, you can make use of the laws that, and in particular, it's easiest if you use the Hamilton equation of motion. You can make use of the Hamiltonian equation of motion, and this shows you that the time evolution of a system in well, of all the position coordinates is such that if you consider a volume element in this phase space, which so you have a point here, you have a small volume element around it, it evolves in time. F equals m times a, or if you wish the Hamilton's equation, dh dq is minus p point, and dh dp is plus q point. Is q point. Then it is easy to show, and if you wish I can even do it, but it's easy to show that the volume element in that phase space is conserved. So it means that if you have a certain volume, that it doesn't expand or contract. It takes on incredibly bizarre shapes, but the volume is conserved. And this conservation of volume is the thing that helps you understand why actually you uniformly cover all spaces. So all points in phase space are equally likely to be at some point included in a volume that you start. So you start here with a volume, and then you go through phase space, and then every other point in phase space is equally likely to be at some point included in this small, be it deformed volume. Now, that is something that you assume, but in general you cannot prove. There are partial proofs that make it plausible that this is correct. I mean, the partial proofs are no, I wouldn't say unreadable, are only readable to certain people. So there's the famous proof by Sinai that is now already, I think, some 50 plus years ago, or maybe just 50 years ago. Okay, so anyway, so it's 600 pages, and it only proves a part of this problem, that the so-called ergodicity problem, that effectively the system has a classical mechanical system has the necessary properties that you need to subsequently use statistical mechanics in the sense that you can replace the time average behavior of the system, which is what you would explore in an experiment, by an average over this phase space that is the volume in phase space consistent with the conditions V, E, and N constant. So that is, and there are situations where the proof doesn't hold. So there are certainly systems that behave in a so-called non-ergodic way. So there are exceptions. In quantum mechanics, the situation is I would say equally sketchy, but I'm less familiar with it. But I mean, again, you have things that make it very plausible, that is reasonable, but a general proof that simply says this is the way it is, to my knowledge, doesn't exist. But why do we need this? And so the reason why we need it is because what we want to do is to translate the statement heat flows from hot to cold into a much more trivial statement, namely a system spontaneously goes from a state that is less probable to a state that is more probable. And again, this sounds sounds in a sense is not such a, I mean, it's not quite so trivial statements. You prepare a system in a certain way that it has access to a number of states. You remove a constraint. For instance, you let heat flow, or you let you let the volume expand, and it gets access to many more states. And basically, the situation is that if you then compare the original state with the final state, it is much more probable that the system will be in one of the states corresponding to the final state than in one of the states corresponding to the original state. That is more or less the statements. And so to make that a bit more quantitative, I'll go through the standard arguments again. But I want to say already at this point that the assumption that all states are equally likely to be occupied, so the thing that follows sort of from classical mechanics, is not really necessary to get to introduce a quantity that behaves in all other respects like entropy, and I'll come back to that later. So let me then have a look, and oh, did I manage to mess up? Yes. So, oh, these are the, sorry. I have to be very careful with my notes, because if I can't find it, then nobody can find it. Yes, okay, sorry, of course I put it here. Right. So to get to the next step, this is really the rather elementary argument that you always hear. We have a system that is closed, so it means that total energy is fixed, the total volume is fixed, and the total number of particles is fixed. But for the time being, I don't care about volume and number of particles, I just care about the energy. So I just say the total energy is fixed, but this system has an energy E1, and this system has an energy E2, and the sum of E1 and E2 must be equal to the total energy. So that's the only thing I'll be looking at the moment. Now, the number of states, and now I must admit that, and this is not due to my unclear writing, but due to my unclear thinking, Boltzmann's graph says that we should write the number of states as W, but very often you find the number of states denoted by omega. And unfortunately, as I go, I'll be switching back and forth, but mainly forth between using W and omega as the number of states. I just say it now because as in my notes I've written omega, it is almost inevitable that even if I try to correct now, I'll slip later. So I'll just write then that the number of states of this system would be omega 1 of E1. And I write omega 1 because this may be a very different system than that system. So it is not, omega is not a universal function of E. It depends on the atoms and molecules that are there, etc., etc. And then you have the other system, omega 2 of E2. Now you can look at the total system, and now you make an important assumption. You assume that these two systems are essentially uncorrelated. So whether this system is in a particular state doesn't affect what's happening in that system. So if this system is in one state, this system still has access to all omega 2 states, and conversely, if this system is in one state, that system still has access to all possible states. And that means that the total number of states of the combined system is equal to the product of these two. I mean, and of course, you can put all the energy here, you can put all the energy there, and for any realization, the number of the states for the total system is just this product. But of course, the value of the product will depend very strongly on how you divide the energy. In fact, if you make a drawing on a scale that is impossible, and I, for instance, write here 0 and here E, and this is the energy in system E1, and I write here on this axis omega 1, then that quantity, and I really have to explain that the drawing is terrible because the function effect is so steep I could possibly draw it. But for low energies, the number of states is very small. Basically, because if you take an ideal gas, you would have the constant energy surface would be a hypersphere. The larger the radius of the hypersphere, the larger omega 1. So actually, if for an ideal gas, omega would go as the energy of the system to the power 3n over 2 in 3 dimensions. So it's very rapidly, and if n is 10 to the power 23, you see that this is not a really good sketch of that curve. I mean, for system 2, it looks like this. And again, it's not a good drawing. The product, but of course you can't see that from my terrible drawing, the product actually is very sharply peaked at a particular value of E1, and therefore also of E2 is E minus E1. So if you just bring the two systems in contact and you let the energy do whatever it likes, it can be here, it can be there, you'll find that the overwhelming number of the overwhelming majority of all states of the combined system corresponds to a very specific distribution of the energy. Okay? And so now we're going to work on that. We say we want to determine this point. And later, well, I'll just say, although normally you derive that, you'll show that the width of this distribution actually is extremely narrow. It goes effectively as 1 over the square root of the number of particles. So again, if there's 10 to the power 23 particles, then the width delta E over E is of the order of 10 minus 11, 10 minus 12. So it is a very sharply peaked distribution. And so we're going to do that by looking at the maximum of this quantity. And actually what is in this stage more convenient, and later on not just more convenient but even necessary, is that we rather than looking at the maximum of this function, we look at the maximum of this function, the log. By the way, this is an L and that's an N. Okay, good. And this is, we'll also take an L N here. And then we take the maximum. Why is it nice to take the log? Because then I can write this as log omega 1 plus log omega 2. And then we say, and this depends on E1. And all the rest of the energy is in the other one, E minus E1. And I can differentiate with respect to E1 and determine the position of the maximum. And if I do that, I get, of course, d log omega 1 dE1. And then I could write plus d log omega E minus E1 dE1, but I write this as E2 and then write dE2 is minus dE1, and I get minus d log omega 2 E2 dE2 is 0, which means that these things are the same. Now that very much looks, I mean, we know that this must be equivalent to the condition of equal temperatures, because if I bring two objects in contact and no heat flows, the temperatures must be the same. But these things are not the temperatures. However, and now Boltzmann comes in, we know that S is K log W. At least that's what Boltzmann postulated. Well, S is K log omega. And so if I now look at ds dE for system 1, then this is K d log omega 1 dE1. Now, how about this? And here I have to do one step back, but only a small one, if I still can find where it was. Well, it's not very important. In essence, the only thing I have to say is that the change in entropy of a system, ds, was equal to the amount of energy, of heat transferred divided by T. If I keep the temperature constant for a small amount, right, ds is dq over T, where dq is the amount of heat transferred reversibly. And if I do nothing else, no work, constant volume, no exchange of particles, this is simply equal to dE over T. So this is at n and V constant. And that means that ds dE, this is thermodynamics, at constant n and V is 1 over T. So here we have ds dE. And here we have d log omega k d log omega dE. And so if we now combine everything, then you get something that again is well known and almost trivial. Namely that one over T is equal to ds dE, and let's say it 1, 1, 1 is equal to k d log omega 1 E1 dE1. And so now we have a relation between the variation of the log of the number of states and the temperature. And so this means that when we say that heat flows from hot to cold, the only thing we're saying is heat goes from a state with fewer realizations to a state with more realization. And then it sounds almost trivial. Almost. Now, I'd like to say a few things about the Boltzmann hypothesis, S is k log omega, because at this point I didn't derive it, I just said, let's assume that log omega up to a constant factor is equal to S. So it has certain advantages, so we say pro. The first thing is it is extensive. Is extensive, and the reason is the following. If I take two systems, two identical systems, let's take two is easy, then I get that the S for, so this is S with S with n particles, and here S with two n particles, and I don't just double the number of particles, double the volume and double the energy, is equal to k log omega squared, because there's now two identical systems next to each other, and that is 2k log omega. So it's extensive. That's nice. The other thing that is nice, certainly was nice when people started to think about the third law, is that if you cool the system down to absolute zero, and the system has a single non-degenerate ground state, or at least a ground state that has a sub-extensive number of realizations, then you get that S at t goes to 0 also goes to 0. So you get this third law for free. There is one sort of, in a sense, a bit unfortunate thing, and that's this constant k. It would be much better, of course, if you would just say S is log omega, and in other areas you simply say that. Here we can't, and the reason is that actually entropy was introduced in the 19th century before people started to counting states and using the Boltzmann argument, and so entropy already had a dimension, joule per Kelvin. At that time, almost certainly it was calories per centigrade or whatever it was, but I mean, it had a dimension, and in order to couple the new definition of entropy to the old one, you need a conversion constant, and the conversion constant is what's now called Boltzmann's constant at 1.38. Oh, I have the number somewhere else. 10 minus 23 joule per Kelvin. So somehow it's a bit, I always find it a bit sad that Boltzmann's constant is actually named after a conversion factor. It seems a bit, it doesn't really do credit to the man, but at the same time it's a very important conversion factor, because it did enable Perrin in 1910 to actually relate the macroscopic thermodynamic description of systems to the microscopic description, where you take fluctuations statistical mechanics into account. So it is an incredibly important result. The thing is, how do you, I mean, I just say this is that value, 1.38, etc., 10 minus 23. How do you get there? It doesn't, you can't derive it in any meaningful sense of the word. You really, in the end, have to go back to experiment and to for instance use the expression for the entropy to compute the pressure of a gas, compare with the take an ideal gas, compare with the real pressure, and then you get this identification. So at some point you'll always have to feed back to experiment to get real numbers for the relation that you have obtained. The 5 minutes, right? Something like that. That is just enough to say one more thing. That is about the second law and the meaning of the word always, because always in this context depends on whether you're a physicist or a mathematician. Because basically if we have two systems, let's again do the same thing. We have two systems and we bring a small amount of energy, and this system has a temperature T1 and the other system has a temperature T2, and we bring a small amount of energy delta E from one to the other. Now we know how the number of states is going to vary, because if you look at the total number of states of the system, that is then the number of the variation in the log of the total number of states is just log omega E1 plus delta E, E2 minus delta E divided by the original situation, total. And because we can expand, we can write omega t is omega t at E1 plus d log omega t expand. You get something that immediately tells you that d log omega t is delta E times 1 over T1 minus 1 over T2. Now, if I take a truly microscopic amount of energy, just say just a thermal energy, kT. Sorry, because I should have K here. If I have an amount of energy kT, then you immediately can show that the number of states, so the probability of the new situation where I have to transfer the amount of energy delta E compared to the old state, is e to the power 1 minus T1 over T2. And so even if T1 and T2 are not all that similar, you see that this is a number of order 1. So this is something that is not at all unlikely to happen. So you have two systems in equilibrium, some energy goes the wrong direction, who cares? Well, I mean, as I'll say in a minute, you care if you repeat the experiment many times, but otherwise you don't care. But if you now instead take a system where you say delta, so this is delta E is kT. Now we take delta E is very, very small, but it's no longer kT. So just to make it easy, I'll say that it's 4.5 10 minus 12 joule. That is a small amount. We can all agree about that between two systems. And then P new divided by P old. And that's why I cunningly took this factor, is e to the power 4.5 10 to the power minus 12 divided by 4.5. This is actually kT for room temperature 10 minus 21 times 1 minus T1 over T2. And that is e to the power 10 to the 8, sorry, too quick, 10 to the 8, 1 minus T1 over T2. And now you see that even if the temperature difference is either, so for instance that this temperature ratio is 0.99 or 1.01. In one case I get that this factor, if it's 0.99, so T1 over T2 is 0.99, then I get that this is e to the power 10 to the 6th. And if it's 1.01, I get e to the power minus 10 to the power 10 to the 6th. So the probability that a very small but not completely thermal amount of energy flows on is in the wrong direction. So this is going from hot to cold, this is going from cold to hot. The ratio is 10 to the 12. It will never happen. unless you're a mathematician, then you say there's an epsilon probability that will happen. Okay, I think I'll stop here. But I'm happy to answer questions.